Hi everybody, this is Dr. Nigo with a Physics Fundamentals screencast. This one's focused on looking at the effect of frictional forces when you have systems of objects. All right, now remember from our definition before, all right, systems of objects are more than one object that move together. I have an earlier screencast where we looked at drawing free body force diagrams and writing F-net equations and solving problems for systems of objects. And a lot of what we're going to do in this screencast is going to be very similar. All right, so when we run into problems where we have systems, it is vital that you first draw your free body force diagram for each object. All right, once you have that free body force diagram, you need to write your F-net equations for each object. And depending on the system, you might have an F-net equation for one dimension and a different F-net equation for a second dimension. It just depends on the system, but you need to write them all. It's a good practice, right? Once you do that, you need to identify and cancel any action reaction pairs within your system. All right, remember Newton's third law tells us that for every action there is an equal and opposite reaction. So when we have these action-reaction pairs show up in our systems, when we do our free body force diagram for the system and then our F-net equations for the system, those forces cancel out, so we don't need to include them. So it's good to identify them and then go ahead and cancel them out. All right, once you've done that, you need to draw your free body force diagram for the system. All right, not each individual object, but for the system. And then write the net force equation for the system based on that free body force diagram. All right, remember, the system has a total mass, so you need to add up all the masses, and it has a total acceleration. So once you identify the acceleration of the system, that acceleration value holds for each individual part of the system as well. So for example, if you have two blocks connected by a string in an Atwood machine, and you determine that the system's acceleration is 1 meter per second squared, then you know that the acceleration of block 1 is 1 meter per second squared and the acceleration of block 2 is 1 meter per second squared, because no piece within the system can move separately from any other piece or it wouldn't be considered a system. All right, now remember, friction opposes motion. So look for the direction of motion and then for those frictional forces. All right. And it's super tempting, particularly when we have our Atwood machines or when we have our cart and hanger or block and hangers, to think about air resistance, but we're not going to consider air resistance in these systems. It's such a small value because these objects aren't moving through the air that far. It's not relevant to these problems. All right, so friction opposes motion, but no air resistance here. That doesn't mean it's not important, but for these particular problems, we're going to ignore it. All right, so let's try a problem. All right, so as shown, a block is attached to a hanging mass via a pulley. The mass of the block is 0.5 kilograms, and we've got two coefficients of friction. We've got the static coefficient and the kinetic coefficient, and those are going to both be for the block, because the block is going to be dragging along this bench top, and so that's where the interaction between our surfaces are going to be. Remember, we consider the pulley itself frictionless. All right, that's just an accepted key to these problems. So don't worry about the friction there. It's only going to be between M1 and that bench. All right, so we're going to start by drawing our free body force diagram. So I'm going to start with mass 1, which is our block that's sitting on the bench. Let me fix my box a little bit. All right, now we've got two dimensions of forces working here. We've got our perpendicular ones, our normal force up and our gravitational force down, and those are equal and opposite. All right, and then pulling to the right, I've got my tension force. And then opposing that to the left is going to be that frictional force. Now, these are not equal and opposite, right? Because the block is going to be moving because of the hanger. So I know that that tension force has to be a little bit less than my frictional force. All right, for sines, the way we set it up, that tension force is going to be positive and that frictional force is going to be negative. All right, so the net force for our perpendicular forces is going to be the normal force plus the gravitational force, all right? The F net equation for our parallel forces, the forces parallel to the motion, is going to be that tensional force plus that frictional force. All right, so those are our net force equations and our free body force diagram for mass number 1. All right, now we're going to look at mass number 2. Now remember, when we deal with pulleys, we pull that mass up so it's all in one plane of motion. So that means that my gravitational force actually appears to be pulling out to the right. And then on the other side of that is our tensional force due to the string. All right, so in this case, tension will be negative and gravity will be positive. All right, we only have one set of F net equations. So the net force here will be equal to that tension force plus that force due to gravity. All right, now remember, we're supposed to go look and see if we have any action-reaction pairs, and we do, our tension forces. So these are going to be equal and opposite, which means they're going to be irrelevant to the system as a whole. All right, so let's look at the free body force diagram for the system. All right, we're going to have a gravitational force this way, and then a frictional force this way. And because the object is moving in the direction of the hanger, all right, then we know that that Fg force must be greater than our frictional force. All right, so for sines, we're going to get a positive sign for that gravitational force and a negative sign for that frictional force. So F net for the system is going to be equal to that frictional force plus that gravitational force. And again, this is going to be negative and this is going to be positive, and our F net should also be positive. So this is going to be our free body force diagrams for each individual piece and then the system as a whole. Okay, so what is the minimum mass of the hanger, which is M2, needed to move the system? So the system is not moving yet, so that means we're going to be looking at static friction. All right, so for this object to move, then I need that gravitational force to be greater than my static frictional force. All right, so the first thing I'm going to have to do is figure out, well, what is that frictional force? All right, so I'm going to start with frictional force static is going to be equal to the static coefficient times the normal force, and this again is of mass 1. Okay, so that frictional force is going to be equal to 0.6 times the object has a mass of 0.5 kilograms, so its normal force will be 5 newtons. So my frictional force is going to be equal to 3 newtons. All right. All right, now I know that I need the Fg value to be just slightly greater than that frictional force. So I'm going to figure out what the mass would be for it to be equal to that frictional force, if that makes sense. So in other words, I know that gravitational force is equal to mass times gravity, and I need that to be equal to 3 newtons, because that's going to be right where we can start moving the object. So the mass times gravity, 10 meters per second squared, equals 3 newtons. That means that mass 2 needs to be greater than 0.3 kilograms. All right, so if I can get it to at least 0.3 kilograms, it'll start to move. Okay, all right, now next part, right, says once in motion, what is the acceleration of the system? All right, so that means we're going to be dealing with the kinetic friction component. All right, so I know that the net force for the system is equal to my frictional force kinetic plus that gravitational force. All right, now I'm going to assume that that second mass is slightly greater than 0.3, so I'm just going to make it 0.31 kilograms so that this system will be in motion. Okay, so I know that the net force of the system is going to be equal to the kinetic coefficient times the normal force of object 1 times the mass of object 2 times gravity. All right, so F net system is going to be equal to, what was the F? All right, so the coefficient was 0.4. And again, we've got a 0.5 kilogram object, so 5 newtons for the normal force. All right, and this is going to be negative. This is going to be important. I got to pay attention to that. Plus 0.31 kilograms for the mass times 10 meters per second squared. All right, so the F net of the system is going to be equal to 3.1 newtons, there's my Fg, plus a negative 0.45 times 5 newtons. All right, if I plug all that in, I get an F net of the system that's equal to 1.1 newtons. So there's the net force acting on our system. All right, I know by Newton's second law that F net also equals mass of the system times acceleration of the system. So that's all going to be equal to 1.1 newtons. All right, I need to multiply the mass of the system. I need to calculate the mass of the system. All right, so I have 0.5 kilograms plus 0.31 kilograms times my acceleration, and that's equal to 1.1 newtons. So 0.81 kilograms times acceleration, 1.1 newtons. So that means my acceleration is going to be equal to 1.36 meters per second squared. All right, do not forget that this mass is of the system. All right, so you have to take both masses and add it together. Do not just do the 0.31 kilograms, the M2. You got to do both. All right, and that will tell us the acceleration of our system. Okay, hope that is useful.